uh, you we saw that, and today we are going to see Liouville's theorem and extended version. Okay, so what is extended version? The extended version is the following. So let f be an entire function, and what is the property of this function? That and for some integer n bigger than or equal to 0, we have, suppose we have mod of f of z is less than or equal to a plus b times mod z power n for some constant, or yeah, so for some constants a and b, then, and sorry, so let me write, we have some constant a and b such that this is true for all z in C, then what we can say is that f is a polynomial of degree at most n. Okay, so this is a very interesting extension of Liouville's theorem. So it says that suppose I have an entire function and I have an integer n bigger than or equal to 0, where it tells me that the growth of my function is at most like mod of z power n, then my function has to be a polynomial of degree at most n. Okay, so here clearly, for example, if you take n equal to 0, then you get that your function is an entire function which is bounded. So therefore, you will get that your function will be, by consequence of this theorem, you will get that it's going to be a polynomial of degree at most 0, and therefore, which means it is nothing but constant, right? So you see that this extends our Liouville's theorem, right? All of you agree to that?
Yes, sir. Yes, sir.
So, in fact, if you even think of a polynomial of degree n, then you can, of course, say that, let's say, the polynomial is of degree n, then you will be able to see that the growth factor for that polynomial is actually z power n, some constant times z power n. So, whatever is the leading coefficient, together with that, you can adjust some more terms, and you will be able to say that the growth is actually given by that, the leading term only, because if you think of all other terms, all of them are going to be dominated by this leading term mod z power n. Okay, because if you take mod z bigger than 1, then naturally mod of z power n minus 1 is just less than mod of z power n. So therefore, whenever your mod z is bigger than 1, you can clearly understand that mod z power n is the leading factor, or like that's the dominating factor. And even if your mod z is less than or equal to 1, it's a polynomial, means it's an entire function, so yeah, it's a continuous function on a closed and bounded set. It's going to have a, it's going to be bounded. So therefore, eventually, effectively, what you will get is that the function is going to be like bounded anyway in the unit disk and outside the closed unit disk, and outside the closed unit disk, it's only growing as per mod of z power n. So whatever is the leading term. Okay, so this is what we are getting from Liouville's theorem. So the proof will be quite similar, in the sense that in the last case we were, if you remember how we proved Liouville's theorem, we used the Cauchy estimate. So here also we are going to do that thing only. So what did we do in the last case, in the proof of Liouville's theorem? So we said, since it's an entire function, we chose any point, and we just wrote down the power series expansion, and this power series expansion was valid everywhere. Okay, and then what we showed is that all the non-constant terms are equal to 0. And here also we can do the same thing. it's an entire function, so you can even think of taking the point 0 and writing a power series expansion around 0, and then we will show that all the coefficients for means for all the coefficients where the index is bigger than or equal to or bigger than n, all of them are going to be equal to 0. Okay, so the proof is going to be absolutely the same. Okay, so uh, we write a power series expansion of f around 0. So what does that say? So let say f of z equal to summation n bigger than or equal to 0, or if let me write k bigger than or equal to 0 if k at 0 divided by k factorial z power k. So this is the power series expansion that we have around 0, and this power series expansion is valid in throughout the complex plane. Okay, so now we show if k at 0 is equal to 0 for all k bigger than n. So if I can show this, then will you agree that we are done?
Yes, sir.
Yes.
Yeah. Okay, so now as you have already seen, I'm just going to use Cauchy estimate. Okay, so now for any, let's say, row positive, we know from generalized Cauchy integral formula that this kth derivative of f at 0 divided by k factorial was nothing but this thing, that integral, it was in the integral was over, let's say, gamma rho and f of z divided by z power k plus 1, right? So this is what we had, and so essentially actually I should not write this, I can directly apply the Cauchy estimate. We know, let me just erase this. So Cauchy estimate I have on, we know from Cauchy estimate that mod of f of k at 0 divided by k factorial is nothing but, what was the Cauchy estimate, tell me? The Cauchy estimate was that this is less than or equal to sum divided by r power k. So here rho power,
From 9 to the power k.
yes, is in, means what was m? M was an upper bound, right? So rho power k. So here m is given by this quantity. So therefore that is a plus b into, and I am taking my rho, means so my mod z can be at most rho. So therefore I can take, this is bigger than 1 even. So this is a plus b to the power rho power n. Okay, so this is what we get from Cauchy estimate, and so for n bigger than k, sorry, k bigger than n, we get uh, mod of f k and 0 divided by k factorial, it goes to 0 as rho tends to infinity. So if I take higher and higher values of rho, I get that for k bigger than n, the bound is going to go to 0. So therefore mod of fk divided by f, the k derivative of f at 0 divided by k factorial is going to go to 0 as rho tends to infinity, but this is a legitimate complex number, so therefore it must be equal to 0. It can't be non-zero because then the absolute value will be positive. So we have f k at 0 divided by k factorial is equal to 0 for all k bigger than n. Hence, is it clear to all of you?
Yes.
Yes, sir.
No, it was, you see, the proof became essentially effectively one line. In fact, there is absolutely no difference in the proof whether you write this one or you write Like this includes, of course, proof of Liouville's theorem. So here, if, as I said, this is extended version. So the proof is very simple. The moment you take this uh, Cauchy estimate and use the power series expansion. Okay. So fine. So I okay. So this is of course not the only possible proof. You can have several proofs. One can prove it by induction and all of that. Okay. But anyway, we have this. Now, now that I know about Liouville's theorem, I want to prove one statement which is very important in the sense it's not a statement rather which is used in complex analysis but rather used in general in algebra. So let's call the fundamental theorem of algebra. Okay, fundamental theorem of algebra. So anybody knows what is fundamental theorem of algebra?
Yes, sir.
Yes, what is that?
Every algebraic
Any algebraic equation of
every
quantity
algebraic
and
polynomial in C has a root in C.
What is algebraic polynomial? What do you mean by algebraic polynomial?
A naught plus A1 Z plus dot dot N Z to the power N.
Okay. Yeah, so it says that any non-constant polynomial in a polynomial over C has a zero in C. Okay, so that means if I take any polynomial with complex coefficient which is non-constant, then it must have a zero in the set of complex numbers. Okay, so in like for example in field theory language, you will say, for instance, that complex numbers are algebraically closed. Okay, so this is something which you probably have seen in algebra, this statement. So we give one proof which like there are again several proofs of fundamental theorem of algebra, but using this statement about Liouville's theorem, it becomes very easy. Okay, so proof. So uh, let uh, suppose this is not true. This is not true, and f be a non-constant and non-vanishing polynomial over C. So I take a non-constant and non-vanishing polynomial over C, and then I am going to get a contradiction. Okay, so that is, what do I have? F of z is not equal to 0 for all z in C. Fine. Now the moment my little this function little f of z is not equal to 0, I am going to consider the reciprocal of this function, and that's going to be an entire function as well. Okay, so these are usual drill that whenever you have a function which is non-zero and the function is differentiable, the reciprocal of that is also going to be differentiable. Okay, so the function capital F of z defined by 1 upon f of z is an entire function. All of you agree to that?
yes, sir.
Okay, so now one thing which I would like to mention here. So this I have already explained in kind of when I was discussing about polynomials. So here I will write this that since f is non-constant, so that means what it has some means like some positive degree. So let's say it has degree n which is positive, then you have this power, the leading coefficient is z power n. Then I already told you orally that f of z, like the polynomial, grows like some constant times mod z power n, so that's the leading factor. So effectively what I wish is that since f is non-constant, we have mod of f of z going to infinity, as mod z tends to infinity. Okay, so this is something which one can show, and I'm not proving this. If you wish, you can try doing that. So you can also, like for example, you the moment, so for example, if you write f of z as a naught plus a1 z so on and so forth, a and z power n. Of course, I am interested to understand the behavior of this guy as mod z tends to infinity. So for my safety, I can take mod of z is bigger than 1. Okay, so now if I think of this thing, mod of f of z, then I can, of course, here since I need my function to go to infinity, I need actually a lower bound. Okay, so what I am going to do here, an is not equal to 0. So effectively, what is to be done is that you take one part of this thing. So I can separate z power n, and then you can keep the other things, whatever a naught plus a1 z plus, or here I was having an, but it doesn't matter. So, and then an minus 1, z power n minus 1. So let me guess this, plus let's say an minus 1 z power n. Okay, now the point is this guy. Okay, uh, let me see, what do I want to say. So let me just have an separately. So an z power n. So my function I write like this, f of z in this way, and then what you can say is that this guy increases much faster than this guy. Okay, so therefore what happens, for example, this guy, so no matter what is the sign of this part, okay, so this term is going to dominate, and therefore you will get that mod of f of z goes to infinity as mod z tends to infinity. Okay, so if you wish, okay, so let me just in fact give you the proof instead of just telling you orally. Okay, so why this is true. So for example, if I have f to be a linear polynomial, so for example, if f of z is equal to az plus b, so clearly mod of f of z tends to infinity as mod z tends to infinity. Okay, so for one variable polynomial, this is clear. And now what I am going to do is that if f is means if has higher degree, then I am going to write f as z into gz plus some, let's say, some constant. Okay, so f0 where gz is a uh, polynomial of degree n minus 1. Okay, so this is what I can have. And now why did I write like this? I wrote it like this because I can see that g of z is nothing but f of z minus f of 0 divided by z minus 0. So this is my g function. Okay, and of course g is a polynomial. So here itself you can see that my g goes to, so anyway, this I really don't need this one. So g is one polynomial, and which is of degree n minus 1. We know mod of gz tends to infinity as z tends to infinity. So by induction hypothesis, let's say, and hence here I have this term going to infinity, this term going to infinity. So clearly, when I take absolute value, the product is going to go to infinity, and this is just merely a constant. Okay, so hence mod of f of z tends to infinity as mod z tends to infinity. Okay, instead of writing as z power n, so I get this, but of course the leading factor, which I was trying to tell you, for a polynomial of degree n, the leading growth factor is going to be some constant times z to the power n. So anyway, so how do why this information is relevant? The information is relevant for the following reason. Here I have mod of f of z is bigger than, is going to infinity as mod z tends to infinity. So this implies there exist, let's say, r positive such that mod of f of z is bigger than or equal to 1 if mod of z is bigger than r. Okay, so this is just the property that mod of f of z tends to infinity as mod z tends to infinity. This implies that, for example, if I want, if I say that my mod of f of z needs to be bigger than 1, then at least there will be a threshold after which my mod of f of z has to be bigger than or equal to 1. Okay, so this is what mod of f of z tending to infinity means. So I have this. Now once I have that, what do I get is that, so this implies for all mod z bigger than r, we have mod of capital F of z is less than or equal to 1. Do you all agree to this?
Yes, sir.
Yeah. Now this capital F of z, this is a holomorphic function, and this is less than or equal to 1 for mod z bigger than r. Moreover, since capital F is continuous, we get mod of f of z must be less than or equal to m for some for okay, so we get, let me write like this, there exists m positive such that mod of f of z is bigger than m for all mod z less than or equal to r. Because mod z less than or equal to r, this is a compact set and I have a continuous function, so this must be bounded. So or closed and bounded set, whatever you want to say. So this is going to be bounded. So there exists an m positive, so that mod of f of z is bounded above by m. And once I have that putting together, so we get mod of f of z is less than or equal to 1 plus m for all z in C. Do I get this? Yeah, agreed.
Yes, sir.
So therefore, I am getting that capital F is a bounded function. And on the other hand, I got also that since little f was non-vanishing, capital F was an entire function. So what can I say about capital F? So
Constant.
by Liouville's theorem, capital F of z must be constant. And if capital F of z is constant, which is just reciprocal of 1 upon f of z, this implies f of z must be constant. And this is a contradiction. Okay, so we got the contradiction because we started by saying little f is non-vanishing, so that must not be true. So therefore, every non-constant polynomial must have a 0. Clear to all of you? Yeah. So the proof is very simple. Essentially, it uses nothing other than the two observations that bounded entire functions are constant, which is Liouville's theorem, and the observation that for polynomials, mod of f of z goes to infinity as mod z tends to infinity. Okay. So this is one key property of the polynomials that we have used over here. Is it clear to all of you? Yeah.
Yes, sir.
Okay, so here I use this crucial property that since f is a non-constant polynomial, I have this thing. So this actually, this characterizes polynomials. Okay, so in fact, the converse is also true. So what I'm trying to say here, theorem: if f is an entire function such that mod of f of z is tending to infinity for all, sorry, as mod z tends to infinity, then f must be polynomial. Okay, so the property that mod of f of z tends to infinity as mod z tends to infinity, this is so fundamental that actually this characterizes the polynomials. Okay, so that's a very interesting result. So not only that polynomials have this property, but rather polynomials are the only functions having this property. Okay, so again here I would like to mention that this mark, this is not true for real C infinity functions. Okay, so here entire function or like complex entire function means holomorphic functions which are holomorphic on whole of C. For those functions, this is true. Okay, so if I just have a function which is, let's say, C infinity on set of real numbers, this will not be true. Okay, so for example, you can take f of x equal to e power x square. Okay, so then clearly this is not only a C infinity function, this is a power series. So this is actually an analytic function. Okay, so when I just see here on the real line, it does not give us the full picture. Okay, so here this function goes to infinity in absolute. Anyway, this function is positive when I look at only on the real line. So this non-negative positive, yes. So this function goes to infinity as mod of x tends to infinity. But as I said, this function is not a polynomial clearly. And here, as I said, so this example in fact shows you that if you just look at one function only at the real line, then the picture is not complete. Okay. So, for example, even though this particular from the theorem, what I get is that this exponential x square, this is an x, or if I would have thought of exponential z square, this would have been an entire function, which is clearly not a polynomial. So what you would have got is that, okay, even though on the real line, as you go towards plus infinity or minus infinity, this function tends to plus infinity, that's true. But on the complex plane, if you see this function and you try to approach infinity from several other direction, let's say along the y-axis, then this function is not going to tend to plus infinity. Okay, so is this clear what I'm trying to say? Yeah, looking at only the real numbers do not give you the complete picture. Okay, so this function of course tends to plus infinity as x tends to plus infinity or minus infinity on the real line. But for example, if you think of this function as a function defined on C, this does not go to plus infinity or minus infinity. Sorry, in absolute value, this does not go to plus infinity as mod z tends to plus infinity. Like for example, you can go towards plus infinity in like mod z. You can take the modulus tending to plus infinity along y-axis, then you might not have this phenomenon. Okay, is it clear what I'm saying?
Yes, sir. Now clear.
Okay, great. So you need to be careful where you are applying the result. It's not true, for example, if your domain is just R. Okay.
So what about e to the power z?
Sorry?
What about e to the power z?
E to the power z, that is also not, that's not going to go, right? Because if you remember when I told you about the exponential function, I was telling you that the exponential functions are periodic, like on each strip of, let's say, width 2 pi, it was taking same value, remember? So I told you, let's say if I draw a strip like this, so whatever the value is taken here, the same value will be taken here, right? So as you go towards plus infinity, means like as the modulus goes to plus infinity along y-axis, you will see that several values are getting repeated again and again and again. So therefore, clearly, you cannot say that mod of f of z really tends to plus infinity. Okay, so that's not true. Okay, in fact, on the y-axis, your points are only of the form e power I theta. Now, in absolute value, they are even 1. So, there is no question of going to plus infinity. Right?
Yes, sir.
Okay, great. So let's prove this characterization of polynomial. Okay, so here I am going to use one statement which we will come back to later, and then we will first complete the proof, and then we will come back to the lemma. Okay, so what is the lemma that I need? I need a lemma. So let D be a domain, and f belongs to h of d. So that means it's a holomorphic function such that f is not identically 0. If is not identically 0, then f has only finitely many zeros on any compact subset K of D. Okay, so what it says is that if you have a holomorphic function which is not identically 0, it can have only finitely many zeros on any compact subset. Okay, so in fact, therefore, for example, okay, we will see why I want, like how I want to say this. So yeah, so what am I saying here? I am saying that I have a domain, I have a holomorphic function which is not identically 0. Then if you take any compact subset of that particular set, so even your D could be whole of C. Okay, so then in that domain you can only have finitely many zeros. Okay, so that's the lemma which I want to use here to prove my result. Okay, so we will see how this lemma is proved a little later, but let me first complete the proof of the theorem that I want to say, and let me also make another remark with respect to this lemma, is that this lemma again does not hold, again does not hold. So in R, if I think of let's say some open set and even C infinity functions on R, then also this is not true. Okay, so the example is same as good old example, that if you take, for example, fx equal to e power minus 1 over x for x positive and 0 for x less than or equal to 0. If you think of this function, then f has f is identically 0 on, for example, identically 0 on minus 1 to close 0. So in this interval it has, this is identically 0, so there are infinitely many zeros, but f is not identically 0 on R. Okay. So clearly these are some of the very important differences between complex analysis and real analysis. Okay, fine. So let me quickly try to complete the proof. Okay, so here I have an entire function, and this is going to mod is going to plus infinity as mod z tends to plus infinity. So I have to prove that G must be a polynomial. Okay, so that's good. So now first of all, let us try to observe the following thing. So since mod of f of z tends to plus, so this is proof of theorem rather. So proof of theorem. So since mod of z, f of z tends to plus infinity as mod z tends to plus infinity, so as I said, exactly like previous thing, so there exists m positive such that mod of f of z has to be bigger than or equal to 1 for all mod z bigger than m. So after certain stage, your mod of f of z has to be bigger than 1. Okay, so all good. So here, so therefore anyway the function does not have any zeros since the absolute value is bigger than 1. Now let us consider the complement of this domain. Okay, so consider the closed ball B close 0 m. Okay, so this is the ball that I am going to consider. Okay, so consider this set. So this is clearly a compact set. Okay, so by above theorem, my function f has how many zeros on this compact set?
Finitely many.
By, it's not theorem, it was lemma. By above lemma, f has only finitely many zeros on B0M. So it has only finitely many zeros. Fine. Okay, so let us list all of them. So say alpha 1 to alpha n. Okay, so I'm not saying they're all distinct. So if one function has multiple zeros, then I will just repeat that particular zero that many times. Okay, so now consider a new function g of z. G of z is what? F of z divided by z minus alpha 1, so on and so forth, z minus alpha n. Okay, so this is a function which is f of z divided by this, and now what I get, recall my f was an entire function, so g is holomorphic except possibly uh, at alpha 1 to alpha n. That's the first thing. And even then, what I can say nevertheless is that, you see, f was already vanishing at this alpha 1 to alpha n's, and I have just divided by those factors. So what it says, essentially I have cancelled the zeros. Okay, so this is holomorphic except possibly at these points, but nevertheless g is continuous everywhere. Do you agree to this?
Yes, sir.
Yes, so the problems were like clearly here the problematic points at alpha 1 to alpha n. Perhaps it's not continuous, it's not holomorphic there, but nevertheless it's continuous, because if you just look at a neighborhood of alpha 1 where none of the other alpha i's are belonging, so there clearly the rest of the function is continuous, and f of alpha 1 is equal to 0. So you are just going to this is just going to get cancelled, so therefore I will get g to be continuous everywhere. Now g is a function, holomorphic function, uh, means a function which is holomorphic except possibly at finitely many points, and it's continuous everywhere on C. So what can I say about g? Yeah,
Holomorphic on
Right.
whole
Holomorphic
world.
everywhere.
exactly. So this is g is holomorphic everywhere. So by Morera's theorem, by or by corollary of Morera's theorem, whatever you want to say, corollary of Morera's theorem, we get g is entire. Okay, great. Now g is an entire function, fine. Now what can I say about g? I have cancelled all the zeros of f, right? So effectively what do I have? So we also have that g is having g is non-vanishing
Non-vanishing on B0.
everywhere on even C. On B0M anyway I had eliminated these zeros, so from F. So on F, on ball B0M it's non-vanishing, and F to start with I took mod of f of z is bigger than 1 whenever mod z is bigger than m. So clearly f does not have a 0, and
Yeah.
g is defined by f over something. If f does not have, like if f does not vanish, then g cannot vanish. So therefore g is a non-vanishing function. Okay, great. So now that g is non-vanishing, what we can say, we get that if I consider the reciprocal, similar kind of trick, then we get that h of z defined by 1 upon g of z is a is an entire function. Listen, this is also an entire function. Fine. Now that I have this particular thing here, let us try to notice what I can say about h. Okay. So about h, I have the following information. First of all, for mod of z bigger than m, what can I say? My f of z was bigger than 1. Okay. And my h is defined to be 1 upon g. So for this mod of h of z, carefully notice this is equal to mod of z minus alpha 1, so on so forth, z minus alpha n divided by f of z. Now mod of f of z is bigger than 1, so that means 1 upon mod of f of z is less than 1. So therefore here all I have is the numerator that I need to take care of, and as we know this is just a polynomial, so the numerator grows exactly like some power of z, means z to the power n. So this is less than or equal to some constant times mod z power n. Okay, so because if you write down a polynomial, you can just take out mod z power n, then whatever the factors are going to remain, each of them except for the constant term, each of them are going to go to 0 as mod z tends to infinity. So therefore what I can say that this whole numerator is bounded above by some constant times mod z power n, and the denominator is anyway was it means f of z was in absolute value bigger than 1, so 1 upon f of z was less than this. Fine, so h of z is bounded above by this for all mod z bigger than m, and again h is continuous, so there exists some let's say k positive such that mod of h of z is less than or equal to k for all mod of z less than or equal to m. I can say this.
Yes, sir.
Yeah, this is just using that on compact set closed and bounded function, continuous functions and bounded. So overall what do I get? Hence for all z in C we have mod of h of z is bounded above by k plus c times mod z power n. Do you all agree to this? Yeah.
Yes.
So this bound c times mod z power n was for mod of z bigger than m, and c times and k was the bound for mod z less than or equal to m. So I can just add both of them, which will work as a bound for all the z. Fine. Now if I have this bound, what can I say about h? Tell me.
That is
Operator
bond
of degree at most n.
and
Yeah.
also.
By extended whatever extended Dewey's theorem. Dewey's theorem. We get h is a polynomial of degree at most n. Fine. H is a polynomial of degree at most n. That's all good. Now, if h is a polynomial of degree at most n, my next claim is that h must be a constant polynomial. Okay, so why h must be a constant polynomial? Because, for example, see how my h is defined. My h is defined as 1 upon gz. Now the numerator never vanishes, right? Numerator is just 1 over here, and g was an entire function. So h is reciprocal of an entire function. So therefore g is not vanishing. Okay, this is at most n, but h is non-vanishing. All of you agree to that?
Yes, sir.
Yeah, because it's just reciprocal of something which is which is some finite quantity. So g is non, but h is non-vanishing. So this implies what? H is a polynomial which is non-vanishing. That means what can I say about h?
H is constant.
This implies h is constant. Good. So this is, so h is a constant polynomial. Now what was h? Come again. H was some z minus alpha 1 so on so forth z minus alpha n divided by f. So this implies z minus alpha 1, so on so forth, z minus alpha n divided by f is constant. So that implies f is polynomial of degree n. Clear? Yeah.
Yes, sir.
So therefore, now I have proved that now I have proved that if I take any uh, function which grows to, like when you look at the growth, and you can say that as mod z tends to infinity, the functional value in absolute value is also going to go to plus infinity, then you will be able to say that it's only the function has to be a polynomial. Okay, so this kind of growth is something which characterizes the polynomials. Okay, so therefore we are done with the statement that if I have any entire function whose growth is like that, as mod z tends to plus infinity, we have mod of f of z tends to plus infinity, we must have f to be a polynomial. Okay, great. So I am left to prove the lemma, right? So I need to prove this lemma, and before proving this lemma, like I can prove this lemma independently, but rather I am going to mm, prove a stronger theorem, for instance, and then we will get this as a corollary. Okay, so what do I want to prove now? So uh, proof of lemma follows from the following theorem as a corollary. Okay, so let me see what is the corollary that what is the theorem that I want to state. So here goes the theorem. So this is called identity theorem. Identity theorem, or in some books it is also written as uniqueness theorem. Okay, so what is this identity theorem or the uniqueness theorem? Let me now write it down. So let D be a domain. So domain means, again remember, it's an open connected set, and f is a holomorphic function on this domain. Suppose there is a sequence of distinct complex numbers zn such that f of zn is equal to 0, and this sequence of zn converges to a point z0 for some z0 in D, then f must be identically 0. So what it is saying? It is saying that suppose you have a domain and you have a function. Suppose your zeros of, like, you have some set of zeros. Suppose those set of zeros have a limit point inside your domain, then your function is going to be identically 0. Okay, so in other words, people say it in this language that holomorphic functions, zeros of holomorphic functions are isolated. Okay, so in the sense the zeros of a holomorphic function cannot have a limit point in the domain. Okay, so if there exists a limit, like for non-zero function. So for example, if you have a function which is vanishing um, on a certain number of points, and those points have a limit point inside the domain, then you will be able to say that your function actually vanishes identically. Okay, so once I have this statement, which is called the identity theorem or the uniqueness theorem, well, you get the lemma just essentially um, in one line. Okay, so why it is called the identity theorem or uniqueness theorem? So the reason being that, for example, suppose I have two functions f and g which agree on a set of points having a limit point in the set D, then you will be able to say f is identically equal to g. Okay, so the choice of function has to be unique, provided you have equality of two functions at a certain set of points which are having a which are having uh, zeros
Set of
on, yeah, a set of infinite set of zeros having a limit point within my domain. Okay, so if you remember, at some point of time I was telling you, so we know this identity, cos square x plus sine square x is equal to 1. This is what you know for all x in R. And if you remember, I had told you that this identity is going to be true also in complex numbers. You remember this? Yeah.
Yes, sir.
I said
yes,
that
sir.
identity
Yes, sir.
of trigonometric functions that you have seen before, like cosine and sine functions, the same identity is going to hold true for complex numbers. And now it should be very evident. For example, this is an entire function or holomorphic function, whatever you want to say, entire function. This guy is an entire function. I see that these two entire functions actually they agree on the real line, and clearly real line has a limit point inside the complex line, so complex plane. So therefore these two entire functions which were agreeing on the set of real lines must agree on the set of complex numbers as well. Okay, so therefore the identities that we had in real life, they get extended to the complex plane, or like accordingly wherever you have the identities to be true, accordingly in complex plane, if they have a bigger set, or in the complex plane you have a bigger domain where those functions can be defined in a holomorphic way, you will get those identities just for free once you know this identity theorem. Okay, so this is a very very strong theorem, and like the proof, of course we will discuss that, but the applications are rather more important. Okay, and like I told you many times, you will hear this, that the zeros of like holomorphic functions are going to be isolated. Okay, so you can't have limit point, for example, inside your domain. Okay, so let us complete the proof of lemma. Okay, so proof of lemma. Once I have this statement, let me quickly complete the proof. So what was the lemma? The lemma was that if I have a domain and a holomorphic function, which is such that the function is not identically zero, then if I take any compact subset, then the compact subset must have only finitely many zeros. Okay, so this is what we need to prove. So can anybody predict how one can prove this lemma? I have to show that
By
inside,
contrapositive.
yeah, by contrapositive. So how do you want to go about it? So let K be a compact set which has infinitely many zeros. Then how can I argue?
Then by the theorem, the function will be identical
Why?
Since it is
because the
compact
compact set
has
has
limit point.
limit points. All
Very
of
good.
its limit points.
Yeah, absolutely. So compact, like for example, compact sets, like here it's of course Rn, but in general, like here, it's actually a criteria. But in otherwise also, like if you have a metric space, you will get compact sets will imply, like compactness will imply sequential compactness, or like if you have Hausdorff topological space and all that. So here I know that sequential compact means if you have any sequence, then that must have a convergent subsequence, right? So here, so proof of lemma. So let K subset D be a compact set having infinitely many zeros. Then say let's say infinitely many zeros xn. Then xn has a convergent subsequence say xnk. So let xnk converges to x, then this implies x belongs to K as K is closed, and then this implies f is identically 0 on D by identity theorem. Is this clear, the proof, to all of you? Proof of the lemma.
Yes, sir.
Yeah. Okay. So the proof of the lemma was quite easy. So let us now complete the proof of this identity theorem. Fine. So what is the proof of identity theorem? So let me see how much time do I have. So will I be able to finish this, or should I do some corollaries first? Okay, let me see. Okay, fine. So let me try at least giving you one corollary first, and then I'll come to this proof. Okay, because the corollaries are, as I told you, some are more interesting. So of course, this lemma is a corollary. Okay, so the above lemma is a corollary of identity theorem. Clearly. And I want to have quickly few more lemmas, few more corollaries. So another corollary, for example, I told you already that D is a domain. F and G are holomorphic functions on D. Suppose there exists a sequence Zn of distinct distinct complex numbers, such that f of Zn is equal to g of Zn, and Zn goes to Z0 for some Z0 in T, then F is identically G on D. Okay. So that corollary proof is immediate. Apply identity theorem on F minus G. Okay, so this corollary is immediate, and that's why I told you this is called identity theorem or uniqueness theorem, in the sense if I have two functions satisfying some certain condition like this, then you will get that they must be the same. Okay, I have already explained you about those trigonometric identities, so those are also applications. Okay, now I want to say I want to give you another corollary. So, if you remember at some point of time, I told you that we will call an open plus connected set. I told you that this we will call a domain. Remember, I said an open and connected
Yes.
set is going to be called a domain. In general, other books also call it region or things like that. Okay, so I said I call it domain for a particular reason. Okay, so what is the reason? The reason being the following. Let D be a domain. So then I have an interesting result. Then h of D, which is the set of all holomorphic function, is an integral domain. Integral domain as in from algebra. Integral domain with respect to pointwise addition and multiplication of functions. Okay, so this is a strong statement. It says that if I have a domain, then h of D is IB. Okay, so h of D is an integral domain. So you must have read about integral domain, right, in algebra course,
Yes.
right?
Yes, sir.
Yeah, so that's why I said, I mean, like that was the reason why I said I prefer to call open connected sets to be like as domain. So it will always remain with you that if I have a domain, then set of all holomorphic functions on that particular domain is going to be an integral domain. Fine. So let me first give the proof of this corollary, then I'll go to the proof of identity theorem. Okay, so let's see. So what am I going to do? I am going to start with two functions whose product is equal to 0, okay, on D. Then I have to show that one of them has to be equal to 0. Okay, so let f comma g belongs to h of D such that the product h times g is identically 0 on D. Okay, so this is actually very interesting. The proof is quite easy. Okay, so what I do is that so let some point, let z belongs to D, choose r positive such that b z r is subset of D. Then if I consider the closed ball b z r by 2, then this is going to be inside b z r, which is going to be inside D. Fine. You agree to this, what I wrote?
Yes, sir.
So why I did this is that I did this because I wanted a compact set. Okay, so that was the only reason. Fine. Now that I have this, we have f times g is identically 0. That implied f times g is identically 0 on B, this compact set bz r by 2. Fine. Once I have this, now clearly, now if g is not, how do I say this? Okay, so now if g vanishes at only finitely many, or let me write like this: g vanishes only finitely many points on b z r by 2, then f must vanish on infinitely many points of b z r by 2. Fine, is this clear?
Yes, sir.
Because
Yes.
overall the product has to be 0, right? So if g vanishes only at finitely many points, then f must vanish on infinitely many points, and this implies that f is identically 0 by identity theorem, or whatever, by lemma, whichever you want to say. Okay, or identity theorem. Okay, and if g vanishes at finitely many points, then again, sorry, at infinitely many points, then again by lemma or identity theorem, whichever you wish, g is identically 0. So whatever the case might be, whether g vanishes at infinitely many points or vanishes only at finitely many points, like that includes that g might not be vanishing at all. Okay, so whatever might be the case, in either of that, I will get either f is identically 0 or g is identically 0. So is it clear?
Yes, sir.
Yeah, is the proof clear? So therefore, I definitely get that if I have two functions whose product is identically 0 uh, on domain, then one of them must be equal to identically equal to 0. Okay, so here again, let me make like a remark and give you an example. So for instance, this is again not true, so this statement is not true in R. So for example, I will take the same function. I think take f of x or equal to e power minus 1 over x for x positive, 0 for x less than or equal to 0. So that means this is identically 0 on the negative real axis on starting from 0, and on the positive axis this is non-zero, and g x to be mirror image of f. Okay, so just take the mirror image with respect to y-axis. So if you take these two functions, of course there is no change. These functions are C infinity functions, and clearly if you take the mirror image, you see one function is identically 0 on the negative x-axis, and the other one is identically 0 on the positive x-axis. So therefore their product is identically 0, but none of the functions are identically 0, even though these functions are C infinity functions. Okay. So therefore, this particular statement, as I wrote, the identity theorem and all this is really an important statement. Okay, so let me see how much I can do, or at least if I can give you a sketch of identity theorem. If I'm not able to complete the proof in the next 10 minutes, I'll try to at least sketch it. So proof of identity theorem. Okay. So what do I have to prove? I have to prove that if I have a domain and I have a holomorphic function, so suppose I have a sequence of distinct complex numbers where the function is vanishing, and with the property that there is a point where these sequence of complex numbers are converging to, and the point belongs to the domain, then the function must be identically equal to 0. Okay. So here what I am going to do is that I am first of all I am going to write down a power series around my power series expansion of my function around z naught. Okay, so first of all note f of z naught. What is the value of f of z naught when I look at the identity theorem?
0.
Why? Why is it 0?
By limiting cycle.
F is identically 0.
Just by if I just think of this as like this is continuous function, so using that I get f of z naught is 0. Fine. Now I can write down the what do you say, the power series expansion. So the power series expansion f of z is f of z naught plus f prime of z naught into z minus z naught plus f double prime at z naught divided by 2 factorial z minus, sorry, 2 factorial z minus z naught square, and so on and so forth. So this term is not going to be there. Fine, all good. So now define, once that term is not there, so define g1 of z, which is what? Which is f of z divided by z minus z naught and f prime of z naught for z naught equal to z naught. Sorry, this is for z equal to z naught, and this is if z not equal to z naught. So I define this function. So what is that function? That function, if you see from here, this is just f of z divided by this quantity. So it starts with, so what is this function? So g1z is actually f prime of z naught plus f double prime of z naught divided by 2 factorial into z minus z naught plus so on and so forth. Fine, is it clear to all of you? Yeah, what is my g1? Clear or not?
Yes, sir. Okay.
Okay,
Yes, it is.
so yeah, so what can I say about this new function g1? Anyway, you have already seen this by means of Morera's theorem also. So what is this g1 function? G1 is also,
Continuous.
this g1 is also continuous, and moreover g1 is holomorphic, right?
Yes, sir.
Isn't it? Holomorphic on D. This is why if you think of by Morera's theorem, you have already seen this, or corollary of Morera's theorem, whatever you wish. Okay, now tell me about this sequence G1 of Zn. What can I say about this quantity G1 of Zn? Yeah, what can I say about this G1 of Zn? Just look at the function and tell me what can be G1 of Zn. Sorry, what is G1 of Zn?
And address not
Sorry,
Dash of Z naught. Is saying F dash of Z naught.
0. G1 of Zn I am asking why it needs to be f dash of Z0 and the point Zn. So Zn's are all distinct points. Okay, only one of them could be equal to Z0, but otherwise all of them are distinct. So G1 of Zn is equal to 0 except possibly 1, except possibly for 1n or 1n. Is it clear? Yeah? Yes or no? Tell me.
sir,
Yes,
A
sir.
dash
So this is equal to 0 for all n. So here, for example, I can, without loss of generality, I can assume that, so let me start here. Without loss of generality, let z of n is not equal to z0 for all n. Anyway, all of them are distinct points, so at most one of them could be equal. So I can assume all my zns are not equal to z0. So therefore, I will get that g1 of zn is equal to 0 for all zn. So then this implies what? What is G1 of Z0 therefore? Tell me what is G1 of Z0? This is equal to what? If Zn goes to Z0 and G1 of Zn's are all 0, then G1 of Z0 will be
F dash.
0.
F prime
Yeah,
of Z.
Zero.
If does not.
yeah, F dash Z0 that is by definition and it's equal to 0 because my Zn converges to Z0. Is this clear to all of you? This last line that I wrote?
Yes, sir.
Yeah, so first of all, that G1, this is the definition, and this part that this is equal to 0 because Zn goes to Z0 and G1 is a holomorphic or continuous function. Fine, so therefore my f double dash Z0 is also equal to 0. So therefore, what is my power series now coming out to be? My power series is not now coming out to be f of z is equal to, so here you see this term is also gone. So therefore my power series is coming out to be f double dashed at z naught divided by 2 factorial z minus z naught square plus so on and so forth. Okay, so higher degree term f triple dashed at z naught 3 factorial plus z minus z naught cube and so on and so forth. Now again define new function g2 of z. What is g2 of z? g2 of z is f of z divided by z minus z naught square if z is not equal to z naught and otherwise f double dash and z naught divided by 2 factorial. This is what I define if z is equal to z naught. So this is my definition of G2. Okay. Now again you see that my G2 function is going to be holomorphic again because this function is holomorphic everywhere and perhaps not continuous only at perhaps not holomorphic only at z0, but this is still nevertheless continuous at z0 because if you just divide f by z minus z0 square and take the limit as z tends to z0, you know whatever the limiting value you are going to get, that is precisely which I have given here. So therefore, the function g is actually g2 is actually continuous. So g2 is continuous and therefore continuous and holomorphic everywhere except possibly z naught. So this implies g2 is holomorphic. So this is by corollary of Morera, by corollary of Morera's theorem. Morera's theorem. Okay, so by now you understand what is going on. Okay, so This is holomorphic, and again g2 of zn therefore is equal to 0 for all n, and this implies g2 of z naught is equal to 0, and which is nothing but f double dash z naught divided by 2 factorial. So therefore what I see is that the second derivative at z naught is also 0, so this guy also goes away. So effectively what do you see? Tell me, what do you see? The way we are proceeding, it is telling
It
us
is all derivatives
all,
0 at z naught.
Zero.
very good, all the derivatives are going to be 0 and z naught. Continuing this way we get all the derivatives, all the derivatives of f are f, all the derivatives of f at z naught is are 0. So all these derivatives are equal to 0. So therefore, what can I say about my function in a neighborhood around z naught? Tell me. So f in a neighborhood of z naught, wherever the power series exists.
Zero.
So f is identically 0 in a neighborhood of z
Z
naught.
naught.
Very good. So I had to show that f is identically 0 in the whole of D. So far, I have managed to show that f is identically 0 in a neighborhood of z0. Now, in all this till now, I have nowhere used that my domain, my means like the set where the function is defined, it's a connected set. So this is what I am going to do next. So my time is up. So I'll just sketch you the proof and complete this part in the next class. So here I am going to define a set of all points in D such that f is identically 0, f is identically 0 in a neighborhood of z. So I collect all such points, and b, I take it to be complement of a. Okay, so here you will clearly see that a is a non-empty set because my z naught is there in a, and you will be able to show that both a and b are open sets. And since their union, so this is a complement means I should write it more clearly, d minus a. So since a union b gives you d, which is a connected set, and both a and b are open with a to be non-empty, we will get that b must be empty, and therefore a will be equal to d. And once a is equal to d, that means I get f is identically 0. So is this clear? The remaining part of the proof. Yeah, so what we are going to do
Yes.
is that we show a and b are open since a is non-empty, d connected. This implies d must be equal to a. Okay, so I cannot have, if I have a connected set, we have, I told you already the definition that we can't have we can't write a connected set as disjoint union of open subsets, but that is what is happening over here. So disjoint union of non-empty open subsets. So since here I can write like this, so, and here I know that a is non-empty, so therefore b must be equal to empty, and that will imply d equal to a, and this will complete the proof. Okay, so I'll stop here for today, and this remaining part I'm going to complete the proof in the next class. Okay, so anyway, you understand the already the idea. Okay, so that's good enough for today. Okay, so let me stop the recording. So are there any questions?